any burning points. I have problems here, of course, but if you guys have something that you're worried about. Does everything make sense? So you guys know the quiz is cumulative, right? Everything all the way back from lecture 1. So I would look at all the lectures and all the P-sets and look at all the stuff that we taught you. So data structures, algorithms, everything, and at least be able to know for every one of them what's the name, what it does, and what's the running time. Proofs and how it does it might be harder, but at least be able to call it as a black box and argue about the running times. So I have a DP problem, and I have a non-DP problem. Which problem would you like me to start with? Okay. Do you guys know the saying of if a woodchucker would chuck wood, how much wood would a woodchucker chuck? Today we're going to chuck wood. So we have a piece of wood that is L meters long. And we have N markings. So say the first mark is at 3 meters. The second mark is at 5 meters, so on and so forth. M3, M4, all the way up to Mn. So we want to cut this piece of wood at all the markings. The thing is, the woodchucker doesn't work for free. If you give it a piece of wood of length L, and you ask it to cut it at some marking, you're going to get 2 pieces of wood, length L1 and L2. The price for this is L1 times L2. So we like woodchuckers, but we also like our wallets. So we want to cut this up by paying the minimum amount of money. Rings a bell? So I'll let you guys think for a minute, then I'll give you the running time, then we'll start talking. So we usually give you running times on quizzes. The running time is why you should know all the problems and their matching running times, because the moment we give you a running time, you can automatically eliminate all the things that don't match and just focus on a few things.
How many pieces do you want it to cut into, or is it just like minimizing?
So you're going to have to cut it at all the markings eventually, but the order in which you cut is important. So if I cut here first, then I'm going to pay 3 times L minus 3. Whereas if I cut in the middle first, I'm going to pay whatever this is, M3 times L minus M3. So we're trying to decide the order. Does this look like any familiar problem?
Very confusing. DP, right?
DP, that is good. I did say that we're going to start with a DP problem, so this is DP. It's a good start. Blackjack?
Yeah, blackjack.
So it is not like any problems on the recitations. So far recitations all did, yeah. So far recitations did prefixes and suffixes. We're going to solve this using a running time of n cubed, which is like the parentheses problem. It should be what you said, but I don't know how to spell that, so we're going to go for this instead. So running time n cubed. The moment I said this, you guys should know that this is the only n cubed problem that we have in lecture notes. So make sure to have those on the cheat sheets and try to understand them, right? Okay, so given that I've said this, you should know the solution now. To make sure everyone is with me, we're going to go through the solution, though. So what is a subproblem? Okay.
And like how to cut it up.
Okay. So this is how you think of it informally. When you write it up, I want to see this. I want to see dp of something means something. So how you fill out your dp table?
Okay.
It's really useful to write this up on your exam before, because one, this will help you write the recursion correctly, and two, if the grader sees this, they might skim over the recursion completely, and then you might have bugs there, we might not see them. Good for you. So this says how you're going to fill out the table, right? dp of something equals something. What's in a dp table? Numbers. It's never how to do something. It's always a number. So it's always the maximum profit or the minimum cost or the shortest distance or the longest something. So it's always a number. So what do we do here?
Start to end dp. The start location to the end location is...
Okay, so we're going to give them indices, right? We usually do I, j, k, and whatever else it takes. So start to end is?
The min cost of cutting that up.
Minimum cost of cutting up the wood board from marking I all the way to marking J. Well, there's a tiny problem here that there's no problem for this big piece of wood. Right? If I can only consider the board from I to J, so if I can only consider the board from marking 1 to marking N, then I get this. So this part and this part get left out.
Can't you just do M0 and M+1?
Exactly. We add fake markings. M0 is 0, and Mn plus 1 equals L. Very good.
Are we assuming that they're evenly spaced?
No. So these are numbers. If they were evenly spaced, I think there's an algorithm. You might come up with a math and say you always cut it up like this. So while we solve this, you guys have candy, right? So you should eat the candy and be energetic and everything. So min cost of cutting up the board from marking I to marking J. I like this. Have this on your exam if possible, because this will make our life easier, and it's going to make your life easier when you get to the next step, which is how do we compute dp of ij? So suppose I'm looking at the subboard from M1 to M4. So I'm looking at only this. How do I compute the best way to cut the board from M1 to M4? What are my options?
The locations you can cut it.
Exactly. So in order to cut this up, I can either make a first cut at M2, and then, so say I make my first cut here, and then I recursively cut this and cut this. Or the other alternative is take the same guy, M1, M2, M3, M4, cut it at M3, and then recursively cut this and recursively cut this. So I'm iterating over all the markings inside the board. Now suppose I'm cutting it. Yes?
Isn't cutting both enough? Oh, actually, never mind.
Yeah, when I recurse, that takes care of it. So suppose I'm looking at M1 through M4, and I'm cutting it at M2. What's the total cost? So what's the best way to cut, given that I know I'm going to cut there?
The sum of the DPs.
Okay, so it's the best way to cut M1 through M2 plus best way to cut M2 through M4 plus the price I'm paying for this cut, right? Not just the sum of the dp's. One more term. What's this term?
4 minus 1 or something. Or the location of 4 minus location of 1.
So
4 minus 1.
not quite, almost.
2 times.
So if I'm cutting a board into 2 pieces, the cost is the product of the length of the 2 pieces. M2 minus M1 times. Yep. Okay, why did I bother doing this? Some people think better with concrete numbers. If that's the case, then, well, give yourself an example. Write some numbers on your sheet of paper. Then see what letters match to what numbers and copy it up using letters. And there you go. You solved the problem. So where are I and j here?
Well, I would be 1.
Okay. So this is I.
That's J.
That's j. Cool. So let's try to write it up now. So in order to cut the board from I to j, what am I doing? So what am I computing? Usually the first word in your subproblem definition is the function that you're going to use. So it's minimum, and I'm going to iterate over something.
dp of I to, I guess would be all of j. Right? So it's dp of I, j, and then you're looking through
So
j.
I'm computing dp of ij.
Oh, no, of j minus, well,
J minus I, like
Yeah.
K, J minus.
well, j minus k.
There's a k, right? I need a new variable for where I'm going to cut up, right? So fortunately, we have a lot of letters in the alphabet. I, J, K, so on and so forth. L, M.
I
So-
plus k. Right?
So let's say that K is the place where we cut to make our life easy. So I'm going to have dp of,
Well, I is the starting point,
okay,
and then endpoint is I plus k. Right?
so where is K, what's K here?
K is an actual number. It's not the offset, it's the actual number. So it should be like I to K. It depends how you define K, I guess.
So I'm going to make my life easy and define K as exactly the marking at which I cut.
Oh, okay, then just k then.
K is this 2 here. And this is easier, trust me. Okay, plus? Okay. And?
Cost. Of
Oh.
M of J minus M of K.
okay,
M of K minus M of I times M of J minus M of K.
Cool.
yeah.
Yeah, other way around, doesn't matter. So now where does K go? We have to come up with numbers for
That's
the loop, right?
between I and J.
So j minus I.
J minus.
It's just 4K and I2J.
Yeah.
Or I, yeah.
So if I have the board from 1 to 4, do I cut it 1?
MI.
Oh.
I can, but that's kind of weird. Because I'm recursing on the same subproblem.
Oh.
By the way, if you try to recurse to the same subproblem, what are you going to get as your running time? Infinite. So let's not do that. So we're going to go from,
I plus 1 J minus M.
so going from I would be bad. So I plus 1. 2,
J minus 1.
very good.
Would it be like M of I plus 1? Just, I don't know what that is.
So K is which marking I'm cutting at. I never want to
Oh.
cut inside the marking. Hell, I don't even know these are integers. So
No, would it be called, okay. No.
So K is which marking? I, J, and K are which marking I'm cutting at. Right, these are the only discrete things I have. This board is all filled with real numbers. So if I want to cut somewhere here, that's a real number. I don't like that. I want to have integers. So my markings help me get integers. I only want to cut at the marking, so I always look at my problem in terms of which marking I'm cutting at. So this always iterates over markings. So this looks very much like the parentheses problem, right? Same subproblems, roughly the same recursion. Turns out that these problems where you're not considering suffixes or prefixes, but rather you're considering substrings are reasonably hard to come by and reasonably hard to solve. So if we give these to you, chances are they're going to be exactly like the parentheses problem, except for the cost function. This isn't what we had in the parentheses problem, right? So you should be prepared to solve problems that look exactly like the parent problem, but might have a different cost function. And this is how you solve them. Okay.
When you say that like the complexity determines which type of DP like example we use, does that mean that like this a problem can be solved using any of the DP like examples? It's just that the only thing that changes is the complexity.
I don't think you can map every approach onto every problem. For example, if you try to map prefixes onto this, you'd come up with a solution that doesn't look at all the possible choices. So your answer would be suboptimal. Okay. So you'd come up with a fast but incorrect algorithm. However, if you take the problem of find the longest increasing subsequence, you can definitely apply this technique to it. It's more general than suffixes or prefixes. So it's going to work, but it's going to be slower. So in theory, what you should do is you have all these techniques. Given a problem, you try all the techniques. You see which ones apply, and out of those, you see which one gives you the best running time. In practice, if we give you the running time, you match it to the techniques that match the running time. You start backwards from the stuff that you know. OK. Does this problem make sense? Sweet. Now let's do a hard problem. Do people remember hashing? You have 1 minute to remember hashing while I erase the board. So suppose we want to implement a set. The way we're going to implement a set is we have n elements. We're going to put them into the set. So for I goes from 1 through n, we're going to insert element I. So first we're going to insert all the elements into the set. And then after that, given a random number, we want to see is it in the set or not. So for some other number, I used n before, so let's use, for some other number f, we want to see is f in the set or is f not in the set. What data structure would you use normally for this? A hash table, right? You stick everything into a hash table, then you try to find the elements. If you find them, then you say yes. If not, then you say no. Well, it turns out that this would take more memory than what we have. So instead, we're going to do this. We're going to have a hash table of m bits. So these are m bits. And say we have a hash function that satisfies uniform hashing. So given any element, the value is anywhere from 0 to m minus 1, and they're all independent. So the way we're going to insert an element is this table is t. We're going to say that t of h of ai equals 1. So this is a table of bits. For every element, we hash the element, and we set the corresponding bit to 1. So we're going to have some 1s and some 0s in the table. Say if this is ei, it hashes somewhere here. OK, so the question is, we inserted n elements into a table of size m. Given a new element, f, where f stands for false positive, f is not one of the elements that we inserted. I want to know what's the probability that the set will say that the element is in the set. So basically the probability of a false positive.
What do we do about collisions?
Nothing.
I mean, is it chaining or is it open addressing? Does it even matter?
So we're not inserting the elements into the table. This table only has bits. The elements are lost completely after we insert them. So the trade-off is this uses a lot less memory. Instead of having to store entire elements, you just store bits. On the downside, you're going to have false positives. Because if I have a different element, say f, if it hashes to the same location, then the set is going to say, yeah, it's in the set. So you get false positives. Will you get false negatives? No, right? Because you start out with a table of zeros, and you only set the table to ones for elements, for the numbers that match to hashes of elements that are in the set. You had a question? Okay. Okay, do we understand the problem before we attempt to solve it?
Probably like 1 over m.
You'd wish? No. No.
It's uniform.
It's less than n over m.
Okay, I like that. So what are you thinking?
I mean, if there were no collisions previously, then it would be equal to n over m. But there are collisions. Probably collisions.
Okay, I'm going to open up a window in your head and tell everyone else the small steps you took to get here. So we have this new number f. How are we going to check if it's in the set or not? We're going to compute h of f, and we're going to check if t of h of f is 0 or 1. F is different from all the other elements. So its hash value is independent from all the other hash values we had before. We don't really care about this anymore after we have the independence assumption. So h of f is just some random position in the table. So the question is, given some random position in the table, will that be a 0 or a 1? How do you know? If I knew how many ones I have in the table, if I have k ones in the table, and automatically this means m minus k zeros, then what's the probability that h of f will point to a 1?
K over m.
Yep. So the hash takes m possible values. K of them are 1s. So the probability that the hash is going to guess a 1 is k over m. So if we knew how many 1s we have, then this is the answer. We know that we're going to have at most n 1s. That's what you're thinking, right? So k is definitely smaller or equal to n, so the answer definitely has to be smaller or equal than n over m. Now, if you're in a rush, you might say, well, we inserted n elements, so we're definitely going to have n 1s here. That is not true. The hashes of all the elements are independent. So there is some probability that two elements will hash to the same value. And as the number of elements grows, that probability also grows. Okay, so now by looking at this, we got rid of this part of the problem. We don't care that there's a new element. We don't care that it's a false positive. All that we care about is how many ones do we have in the table after inserting n values. Well, what's that? That's m times the probability that a slot in the table is 1. Right? The probability that a slot in the table is 1 is k over m. So if we know this probability and we multiply it by m, then we get k. People still with me?
And what does that variable represent? H?
This is k.
Okay.
It represents that my handwriting sucks, basically.
I mean, like, why do we do m times the probability? That's the expected number of ones in the table?
Yeah.
Okay.
Yeah, this is E of k, I guess. So then our final answer is this thing divided by m. So answer is the expected value of k, or you can just think of it as the average value of k divided by m. So this is m times this probability divided by m. So it is exactly this probability. So the thing that we want to focus on is what's the probability that a random slot in the table is a 1.
It's equal to 1 minus the probability that it was never picked.
Exactly. It's the first thing we do. 1 minus the probability that a slot is 0. This is easy, right? Like, this looks easy. But this makes a huge difference. Because once we're here, well, a slot is 0 if none of the insertions made it a 1. And the insertions are all independent. So this is like you're flipping a coin. What's the probability that after you flip it 10 times, you never get ahead? So this is 1 minus. That.
Number of times.
So a slot is 0 means that no number was inserted in it. We're inserting n numbers. So it's the probability that a single number was not inserted in the slot raised to the power of n. So we have n independent experiments, right? Every time you insert a number into the hash function, that's one experiment. The hash function gives you independent values for all the elements. So all the insertions are independent of each other. If in a single insertion you've hit that slot, then you've made it a 1, game over. So the slot is only a 0 if none of the insertions make it a 1. So you take the probability that an insertion doesn't make it a 1, and you raise it to the power n, because that has to happen n times in order for the whole thing to be successful. And the probability that the number was not inserted in a slot is 1 minus the probability that it was inserted. Right? We're doing this again. 1 minus probability that a number hit. Well, what's this probability? Uniform hashing. 1 over m. So this whole thing is 1 minus 1 minus 1 over m to the power n. 1 minus m minus 1 over m to the power n.
Go through this again, like from 1 minus probability of a slot is 0 to 1 minus probability of a number was not inserted in the slot. Please do log in.
Okay. So first off, the point of the problem, it's our problem, right? Don't panic, don't be angry. You're not going to have something this hard on the exam. The point of this is I want to go through probabilities a little bit, and I want to go through hashing and the math behind hashing, because remembering that will be useful. Okay, so now you said you're having trouble with this step? Okay. So let's see. Let's do this here. So we have this table here, right? And we have n elements, E1, E2, E3, all the way through En. How do we put them in the table? We hash each of them, and each of them maps to a random slot in the table. Right? So if these are the slots, then E1 might map here, E2 might map here, E3 might map here, E4 might map here, so on and so forth. So I have arrows, right? Every time I do a hash, that's going to set something to a 1. The numbers don't necessarily map to different slots, because each number on its own maps to a random slot. So these are all going to be 1s, and everything else becomes 0. If no number maps to a slot, it is 0. OK, let's look at one slot, any slot. So say I'm looking at this slot over here. Can you guys see, by the way? OK, so let's look at this guy here. What's the probability that it's a 0? So the probability that the slot is a 0 is the probability that the first number didn't map to it, right? Otherwise, it would be a 1. E1 didn't hash to that slot. E2 also couldn't match to that slot, right? So it's the probability that E1 didn't hash to the slot, and E2 didn't hash into the slot, and E3 didn't hash into the slot, so on and so forth, right? All the way up until En didn't hash to the slot. Does this make sense? Now, these are all independent events, because all the hashes are independent by the uniform hashing assumption. So then I can turn ands into products. So I can say that this equals to the probability that E1 didn't hash into the slot times the probability that E2 didn't hash into the slot times the probability that E3 didn't hash into the slot, so on and so forth, all the way to the probability that En didn't hash. All the probabilities, so since I'm dealing with the same hash function, turns out that all the probabilities are the same. So there, the probability that some fixed number didn't hash to the power n. So this is how I got from here to here. Probabilities and the properties of hashes and hashing assumptions. So you guys should have those on your cheat sheet. And maybe if you have time, review probabilities a bit.
Well, isn't the probability that any given one doesn't hash 1 over m? So if E1 doesn't hash in that spot, isn't that probability 1 over m?
Not quite. You're close, but not quite. So you're saying that the probability that E1 doesn't hash to this slot is 1 over m?
Or I guess it's 1 minus 1 over m.
Exactly. The probability that it would hash here is 1 over m, because it has to pick that one slot out of m possible slots. But if you're just saying all I want is that it doesn't hash here, well, it means it can hash anywhere else. So it has m minus 1 options. It can go to any of those m minus 1 places, just not to that one place. So m minus 1 over m.
That means it's interesting that the other direction, like instead of saying it's 1 minus it, like,
so this,
wouldn't it be just as easy to go the other direction?
No. No. Not doing this makes the problem hard, so that's why we're doing it. This kind of this kind of flipping is easy to do conceptually, but it might make a hard problem into a really easy problem, or at least into a doable problem.
kind of the same thing? I guess maybe not really.
So it is exactly the same in terms of the math, but
Yeah.
computing this without turning it into this is really hard.
Any given slot is 1. Isn't it kind of like what we just said, except if the probability of any one mapping is 1 over m, like mapping to a 1, right? And then you take 1 over m raised to the n, that's the probability of it being a 1 at that one place. Right?
No, not quite. Yeah. Okay, so are we getting this? Somewhat? Yes.
So the probability of false positive, you're saying that's what's the probability that you get a 1? It actually should be a 0. It's because multiple things map to that one slot, right?
So the probability of a false positive is the probability that given a new element, when we hash it, we get the 1. The hash of that new element is independent of all the other hashes.
Why is it simply the probability that you get a 1?
Well, so if I have a new element, I'm going to compute its hash, and I'm going to look in the table. If I see a 1, I'm going to say,
It's a new element.
yeah. So it's something that was not in the set.
Okay.
Okay, cool. Okay, so let's see if we can do a harder version of this. So this probability isn't great, but if we do one trick, we can make this really nice, and this puts together a trick called Bloom filters that is used in all sorts of situations. So for Bloom filters, we still have n elements, and we still have a table of m bits. What changes this time is instead of having one function, we have k hash functions. So when we take an element and insert it, we're taking element I. The way to insert it is we're going to compute its hash value using all the hash functions. And set all the corresponding bits to 1. So insert EI becomes for k in, sorry, for j in 1 through k, the table bit corresponding to the hash function j of the element is 1. So each element sets k bits to 1. Now, how do we check if an element is in the table?
Yeah, just like that.
Since for every element we set all the corresponding k bits to 1, now when we have a new element, we're going to compute the k positions. And if any of them is a 0, then we couldn't have possibly put that in the table. So all t of hj of f have to be 1. So for every element, we hashed it k times and set the corresponding bits. If we have a new element, and by hashing it, we get here and here, but we also get here, and this guy was a 0, well, we know we definitely didn't put this in. So now what's the probability of a false positive?
My first intuition is just raising that to a power. The probability that when you check
Oh, I forgot to say something, by the way. The k hash functions are all, I think they satisfy simple uniform hashing. I'm not sure if that's the right thing, but they all have independent values from each other. So they're all independent. So for any number you give, any hash function returns a value that's independent of all the other hash functions, and they're all 0 through n minus 1.
Why is it not that just raised to something? Because we know the probability. Well, okay, actually, we need to recalculate that.
What's the probability that all of them are
Same,
1,
yeah.
even though you haven't hashed them?
So the false positive, the probability of false positives is the probability that all the k slots that correspond to f are 1s, right? So since the hash functions are all independent, this is the probability that one slot is a 1 raised to the power k, right? Because they're all independent slots. So it's the probability that one slot is a 1 raised to the power k. Okay, so now what's the probability that one slot is a 1? It looks a lot like this problem, right? Except there's a tweak. How many times did we put a 1 in the table? So here we put a 1 in the table for every element. So we have n sets, right? So n times we're going to set t of something to 1. Right? For every element, we have one set. We set one bit to 1. It might have been said before. That's something else. Yes?
So it's raised to the nk.
Yeah, pretty much. So here for every element, we hash it through all the k functions and set the corresponding bits through 1 to 1. So one element generates k set operations. And we have n elements total. So we set nk bits to 1. Does this make sense?
Can two hash functions point to the same slot? Like
Sure.
one, right?
Sure. But they're all independent, and that's the only thing that matters. So every time we set a bit, which bit we set is independent of all the other bits we set. Because all the hash functions are independent, and all the values are independent of each other. So this time we have, the table size is still m, so that didn't change. This time we set n bits to 1. This time we set nk bits to 1. So then the right thing to do is copy this answer and replace n with nk. And if you'd have to write a proof, you'd copy paste the proof and replace n with nk. So this is 1 minus m minus 1 over m times nk. And of course, you should go through the whole thing in your head and convince yourselves that this is true.
So let's say one element is what, k net sets?
Bit sets. So one element sets k bits in the table. Not necessarily different bits, just independent bits. So if you have n elements, altogether they set n times k bits. So you do this thing gets run n times k times. Whereas here, the set operation gets run n times in total. That's the difference in the two problems. Right? Here you have one hash function for each element. Here you have k hash functions. This is hard, right? Well, it's the hardest hashing problem that I could think about, and that makes us go through probabilities and through all the hash stuff. The problems on the exam will be easier. So 1, don't panic. 2, review hashing, review probabilities. If when I said, oh, from the theory, this is what you get, if you didn't understand that, then please review the theory.
Why is raised to the k? Because we did down there, if we replace n with nk, then we just get everything except.
So this thing in here is the answer to the previous problem.
Yeah.
Except you take an n and you replace it with an nk. So this is the probability that 1 bit is set to 1. But here when you're given an element, you're going to hash it through the k functions. You take this guy. You're going to hash it through the k functions, and you're going to check all the bits. So you're going to check k bits. So as long as any of the k bits is a 0, not a false positive. So we need all the k bits to be a 1.
Oh, I see.
What if the hash functions are dependent?
Then it becomes intractable.
And what if like the I think like the way like in this problem the way they are being hashed that becomes dependent, because I think like there were some problems where if something is being hashed somewhere, then the probability like there could be hash functions that would put the other thing in the next slot. Something of this sort.
Yeah, so you want to reduce these problems to independent hashing. If you look at the proofs, all the proofs assume uniform hashing, simple uniform, whatever it takes to get the math down to independence. Because this is the only thing that we know how to solve with probabilities. If everything is independent, then things multiply and add up in the right places, and everything is easy. If things are dependent, then proofs become really, really hard. So whenever you have dependent things, you want to find a way to reduce that to independent things. Okay, is everyone tired, or do you guys really not like this problem? By the way, really cool trick. So this turns out to be a lot better than that, and I think the optimal value of k is around square root of log n. And that gives you some filters with a really low false positive rate.
What do you mean by optimal?
Minimize the false positives.
Oh,
So
'cause
given
it starts
n and
with-
m, pick k so that this thing is minimized.
What was the answer again?
I think it's,
Or actually, regardless of that, what's the percentage of false positives?
it depends on what your n and m are, right? The more bits you can afford.
So, but if you maximize your k, you said you came up with some k that's maximized. Then what's?
I think k is, but
So that if you use that.
let's not do the math. It's really, really good. So these are used for all sorts of practical problems, all the way from branch predictors in processors to databases.
So is it like better than 1%? You know that at least?
Oh yeah, they're for practical uses. This gets you, I think, to 1% of 1% of 1%. So you usually put a Bloom filter before a really expensive check. And the Bloom filter gets rid of most of the false positives. And then you have a few more where you do the expensive check. Okay, does this make sense? Any questions?
Would it be more optimal if you repeated this Bloom filter independently of the other one with more hash functions in that memory structure?
I think doubling the memory size is better. So 2 filters is the same as having 2 n bits. I think doubling gives you better results always. Okay, so general stuff. We're going to have a lot of conceptual questions. So please make sure, again, make sure that for everything that we did, go through the problem, understand the problem, know that there is a solution, know the running time, maybe know how to implement the solution. Don't worry so much about the proof. We're going to have some problems where you have to come up with new things on your own, so get a good night's sleep before the exam. Really, like, if you have 5 hours left and you have to choose between sleeping 5 hours or reading notes for 5 hours, it's not going to help. So caffeine actually helps you stay up, but it decreases your performance. And yeah, so if you're on caffeine, you're not going to think. You can regurgitate stuff, but you can't think. So caffeinating yourself is a...
I thought it was like it gives you concentration or whatever.
So there's an optimum amount of sleep and caffeine combination. If you don't sleep and caffeinate yourself, I guarantee that you will not solve any of the problems that require new algorithms.
Yeah, caffeine just squirts adrenaline in your brain. It doesn't do anything else.
So the thing is, the memory is going to be better. If all you're doing is memorization stuff, then it's going to be better.
Yeah.
So you're going to do well on the pattern matching stuff. But when your brain is panicking, you're not going to come up with new solutions, right? Usually you have a problem, a hard problem, you're thinking about it, and then at some point when you're relaxed, like when you're in the shower or when you wake up, you're like, crap, I found a solution. So the brain finds solutions when it's relaxed, not when it's like, holy shit, holy shit, holy shit. And adrenaline gets it in that mood. That's what it does. And that's what caffeine does in the end. So a little bit of caffeine might help you get up and get you running, but don't caffeinate yourself to not sleep the entire night. That's probably going to make you bomb the hard questions. Okay, make sense so far? Okay, yes?
Are there office hours today or tomorrow? Or are they like breaking?
We're working on a review session. There will be office hours at the scheduled time all the way until the final. So as one last point, like, you're probably looking at optimizing. Now you learned how to optimize things, right? That's what the class is about. So how do you optimize things long term? Right now you're probably looking at, oh, I have finals ahead of me. I have to study as hard as I can, and I'm going to study the things that will give me a better grade so that I can optimize my GPA. Why do you want to do that? You're hoping that better GPA means better job prospects, right? Which means more money, more happiness, and whatever, right? Okay, here's a real-life perspective on this. You're at MIT. You're going to get a CS major, right? MIT, CS. This means that as long as your GPA is somewhere between 4 and 5, you will get an interview. From any company you want anywhere in the world. There won't be a single company that will say, no, I don't even want to talk to you. This is true any company, anywhere. Once you've got that interview, you go there, and what you know determines the outcome of the interview. So if you bomb it, you don't get a job offer, right? So repeat. More companies, more interviews, so on and so forth, right? If you do get it, then you get a job. After you get a job, you go in the state where you become an experienced programmer. The fancy word is senior programmer, but it's really amazing. You've been on a job for 1 month, and all of a sudden you're qualified to apply for senior programmer positions. So this might suggest that an optimal path of making a lot of money is you go work somewhere you don't like for a month, and then you switch your job immediately. That's something for you to think about. In any case, the moment you're here, your GPA is worth nothing. All that matters is what you did on the job, so your experience. So think really well of whether you want to optimize for a good GPA or whether you want to optimize for knowing stuff and succeeding on the interview. And I think that's about it. Any questions on this stuff?
Like, what is the best thing to study, like, among all the materials we have?
Program DP.
So so I mentioned go through the lecture notes and understand problems,
Yeah.
running times, right? Start with DP, then go back to the old material. Also, so I said that you're probably going to have graph transformations again on the final. As of yesterday, this is no longer true. So don't worry too much about that. But if you understand graph transformations, you're better at solving DPs, so you can't ignore them completely.
Can you give us any other hints of what types of problems?
So I said a lot of conceptual stuff and then some new algorithm creation.
Yeah.
It's going to be like the other exams, right? You've seen two before. We're not going to come up with a new problem type. It's like true falses and then a few questions where if you know the theory, then you can solve the problem mechanically or write out the answer right away. And then there are a few problems where you have to think and maybe you'll get it, maybe you won't. If you won't, you want to come up with the best answer that's reasonably fast. And we went through a recitation, in a recitation we went through how you do that.
You mentioned a lot of algorithms. Is there data structure design?
You're not going to design a data structure from scratch or an algorithm from scratch. We usually...
Modify a data structure to optimize for summing something or whatever.
Maybe. So speaking of modifying data structures, what's the stuff that we've modified the most? Yeah, so we studied tree augmentation, right? So if you're going to look at modifying data structures, that's probably something to look over. So by the way, consider this theory stuff. Like, you should at least know, oh, there are BSTs, there are AVLs. This is the difference between them. That's why we like BSTs. That's why we like AVLs better than a general BST. And these are the modifications of BSTs of AVLs, that we studied. Right? We studied a few in lecture, recitation, and P-sets. So I would expect to know them.
Difficulty-wise, would it be close to quiz 1 or quiz 2?
Well, we can't really control that. Like we were aiming for the same difficulty when we were building quiz 1 and quiz 2, believe it or not. We've cut hard problems in general, so we tried to make it easy. But that being said, I don't know. You guys will tell me in 2 days.
Hopefully there would be no graph transformation.
Sorry?
Did you say no graph transformation?
Yes, as of yesterday, we don't have graph transformation problems.
And is there like a slightly, is it like weighted a bit more towards like the material I've done since the second exam? Or
Yeah, definitely. There's definitely more DP than everything else, because that's new stuff.
Yeah.
But we also cover the old stuff. Okay, does this make sense? Anything else? Please finish the candy. And thanks for helping me solve all these problems throughout the term and fixing my mistakes and helping me not look like an idiot. Okay. Good luck on Friday. Eat candy.